Imagine controlling an entire oil refinery. Thousands of sensors, pumps, valves, and motors spread across kilometers of pipelines and equipment. One operator cannot manually manage every single device. So how does a distributed control system, or DCS, make it all work together safely and automatically? A distributed control system is a network of intelligent controllers that monitors and controls an entire industrial process from a single control room. Every sensor is connected. Every valve receives commands. Every motor is supervised. Data flows continuously. The entire plant operates as one coordinated, intelligent system. The word distributed is what makes a DCS powerful. Instead of one large central computer controlling everything, which would be a single point of failure, a DCS divides the plant into separate areas. Each area has its own dedicated controller. If one controller fails, that area stops, but every other area of the plant keeps running without interruption. Everything begins in the field. A pressure transmitter measures pipeline pressure and sends a live signal to the DCS. A temperature transmitter monitors heat at the heat exchanger. A flow transmitter counts cubic meters per hour through the pipe. A level transmitter watches the liquid height inside the storage tank. Every measurement is converted to a 4 to 20 milliamp signal and transmitted continuously. These field signals arrive at the DCS cabinet as analog and digital inputs. An analog input card receives the 4 to 20 milliamp signal from the transmitter, converts it into a precise digital value, and passes it to the controller CPU. Digital input cards handle on-off signals, motor running contacts, valve limit switches, and alarm inputs. Each card plugs directly into the controller rack with its own status LED. The controller CPU executes its control program every fraction of a second. Incoming sensor values are scaled from raw electrical signals into engineering units, pressure in PSI, temperature in degrees Celsius, flow in cubic meters per hour. The CPU then evaluates every control algorithm, compares each value against its set point, and generates precise output commands. This happens in milliseconds, continuously, without human intervention. The most important algorithm in process control is the PID controller. PID stands for proportional, integral, and derivative. Here is a tank-level example. The set point is 60%. The actual level drops to 40%. The proportional term immediately opens the inlet valve proportional to the error. The integral term eliminates any steady-state offset that remains. The derivative term slows the response as the level approaches the set point, preventing overshoot. All three terms together produce a smooth, stable response. Once the controller calculates the required output, it sends commands through output modules. An analog output card converts the digital control signal back into a 4 to 20 milliamp current, driving a control valve to an exact position, say 67% open. A digital output card energizes a relay contact to start a motor, a pump, or a compressor. The field device responds immediately. In the control room, operators never touch field devices directly. They work through graphical process displays on large monitors. A single click changes a set point. The DCS executes the change instantly. Trend windows show how the process responded over the last hour. An alarm banner alerts the operator when any value exceeds safe limits. A faceplate shows the exact status of every controller, set point, actual value, and output in real time. This is the complete closed-loop control cycle. The pressure transmitter measures the process. The signal travels through the input module to the controller. The PID algorithm calculates the exact required output. The analog output module drives the control valve to the precise position. The valve changes the flow rate. The process pressure changes. The transmitter measures again. This loop runs continuously, hundreds of times every second, keeping the process locked to its set point automatically. Critical processes cannot afford to stop. DCS systems are designed with full redundancy at every level. A primary controller and an identical backup controller run in parallel, synchronized at all times. If the primary fails, The backup takes over in under 1 millisecond. The operator sees a single brief alarm. The process never stops. The same redundancy applies to network switches, power supplies, communication cables, and servers. Every measurement, every calculation, and every control action in a modern industrial plant flows through this architecture, from field instruments, through input modules, to intelligent controllers, across the control network, to operator stations and historian servers. A distributed control system keeps complex processes running safely, efficiently, and reliably, 24 hours a day, every day of the year. Understanding this foundation is your first step toward mastering industrial automation and OT cybersecurity.